In this video, I'd like to walk through the first of the propositions in Euclid's Elements of Geometry. You can see up here at the top of the board, I've labeled proposition 1.1. The first number is a Roman numeral that refers to the book number, so it's Euclid Book 1, and then proposition number 1. So we'll refer to this as proposition 1.1. This is lesson 4 in the Classical Liberal Arts Academy's Classical Geometry course. And before you get started with the propositions, you should have studied and memorized or nearly memorized all of the definitions, postulates, and axioms found in Book 1. We're going to begin using them here in Book 2. Now, as you can see, I've already written out all of the work for this first proposition, but we're going to walk through it step by step to learn the 6 parts of a proposition and actually to learn the solution of this first proposition in Euclid. But remember, this all depends on your having previously studied and learned the definitions, postulates, and axioms in Book 1, okay? To begin, since this is our first proposition, we should do a little bit of introductory work. And the first thing that I want you to see up here on the board is that there are 6 parts of the proposition labeled. Part 1, the proposition. Part 2, the exposition. Part 3, the determination. Part 4, the construction. Part 5, the demonstration. And down here, Part 6, the conclusion. For most propositions, all 6 parts will be present when we write out the solution for the proposition. Some propositions don't have all 6 parts, and we'll see why when we get to them. But for proposition 1.1, you can see that all 6 parts are present, and we'll make sure we take time to walk through them so that you understand what each of the 6 parts is, so that you can begin to identify them on your own as you begin working and solving propositions in the future. Now, we inherit the solutions to these propositions. The proposition, which is written here, is a problem for us to solve. In this case, it's a proper problem because there's actually something to do. In other propositions, we'll actually have a theorem which doesn't need to be performed, but needs to be proven. So there's 2 different kinds of propositions. Problems, like we have here in proposition 1, and theorems, which we'll see a few lessons down the road, where we're given a theorem that needs to be demonstrated. Okay? In proposition 1.1, our first proposition is a problem. How do we know that? There's something to be done. And we'll look at that in more detail as we go. All right? So, what is our proposition, our first proposition here? We have it written out here under part 1, the proposition. On a given finite straight line, to construct an equilateral triangle. On a given finite straight line, to construct an equilateral triangle. Okay? That's our proposition. That's what's proposed to us. That's what we're seeking a solution for. Now, all of this solution that's written out here is a traditional solution to this first proposition. It's not the only possible solution. In fact, we could just start with the proposition and say, hey, students, figure it out. How can we solve this problem here? And we can just take out our definitions, our postulates, and our axioms and try to figure out a solution. But we're going to learn this traditional solution, and if you become really interested in geometry, you can take up the challenge of finding other solutions or studying other solutions, and I could explain where you can find resources like that to get really deeper into these studies. We're going to learn a traditional solution for each of these propositions, and what you're going to have to learn as you study them is the proposition, and then each of the 6 parts, the construction, the demonstration, and the conclusion for each proposition. Okay, so as we go through them, you're going to have to take the proposition, understand how to break it down into an exposition and determination, then produce the construction, if it's a problem, if there is a construction, then work out the demonstration, and finally wrap it up with a good conclusion. Okay, so that's how we study propositions in classical geometry. So our first proposition: on a given finite straight line, to construct an equilateral triangle. Just to think about this before we get started, what we're given a finite straight line. We're given a finite straight line, and we're asked to investigate whether it's possible on a given finite straight line to construct an equilateral triangle. And remember, the goal of classical geometry is to build an absolutely certain body of knowledge of magnitudes at rest. We're studying magnitudes at rest. We want to build a knowledge of magnitudes at rest, and we want every piece of that knowledge to be absolutely certain. That's the goal in classical geometry. So the question is, how can we do that? How can we build absolutely certain knowledge? And the answer is by using the elements and reason to solve any problem or demonstrate any theorem. The first thing we want to do with our proposition is establish what's given to us, and to sort of make it more specific for our actual work here in this proposition and in our solution. So what we're going to do is assign specific points and lines or any other figures that are necessary to prepare us to make our construction. So what we're going to do in the exposition is take the general proposition and identify what's given to us and make it more specific for this particular construction and demonstration. So you can see what we've done here is we've said, let the straight line AB be the given finite straight line. We were told on a given finite straight line. That's all we're told in the proposition. Here, we're getting more specific and preparing for our construction. So we're going to identify the straight line AB as that given finite straight line. And in the determination, what we're going to do is determine what is sought. What exactly are we seeking in this proposition? And we can read here, it is required to construct an equilateral triangle on the straight line AB. So using the labeling that we established in the exposition for what's been given to us, we now make it clear. We determine what it is that we're seeking to do and solve in this proposition. We're seeking to construct an equilateral triangle on the given finite straight line AB. That's our task, okay? Now, as I said, we are inheriting a solution to this proposition, a traditional solution that we're simply going to study and learn. But we have to realize that in ancient times, this solution had to be invented or discovered using the elements, the definitions, postulates, and axioms provided in Book 1 of Euclid's Elements. So we have it much easier than they did. We're seeking simply to learn their solutions, not come up with our own. So we have our proposition, our general statement of a problem in this case. We then have our more specific exposition, setting out in clearer terms what's been given to us in the proposition. We then have our determination, where we determine what is to be sought or done in this particular proposition. And now we go to our construction. Okay, in the construction, we're going to try and accomplish this task that's given to us in this proposition, to construct an equilateral triangle on the straight line AB. So what I did to get the construction started was I drew the straight line AB. And you can see that we name a straight line by its points, by the points at its ends or its bounds. So this line here is the given finite straight line AB. A is the name of this point at one end of the straight line. B is the name of the other end point of that straight line. This is straight line AB, which we labeled here in the exposition. Okay? And the challenge for us is to construct an equilateral triangle upon the given finite straight line AB. Now you see here the finished construction, but I want you to sort of unsee it as we get started. Imagine that all you see is the line AB. And remember one more thing. These points and lines and figures are symbols of perfect figures that we are to imagine. Remember, a point has no length or width, so it would be invisible. It's really just a place. But we use a dot to symbolize a point. And so you have to remember that this dot given here for point A is just a symbol of a point. Really, a point is invisible. And you have to imagine an invisible point that we call point A, and an invisible point that we call point B. And then you have to imagine a straight line connecting those points A and B. And that straight line would also be invisible because it has length, but it has no width. Remember that from the definition of a straight line. It has length and connects point A and point B, but it would have no width, and therefore it would be invisible. So this line, AB, is just a symbol of the line that we understand and imagine as we discuss geometry here. So as I said, you have the finished construction is drawn here, but I want you to unsee it and just focus on line AB, because that's all we're given at the beginning of this proposition. We have to figure out how we can construct an equilateral triangle on that straight line. Now, the first thing that we need to do is go to the definitions and look into the definitions and see what is an equilateral triangle. We're asked to construct an equilateral triangle. Let's make sure we know exactly what an equilateral triangle is. And you should always do this. Anytime any of the terms that were defined for us in the definitions is used in a proposition, you should go back either by your own memorization of those definitions or by looking them up, and look up the term and make sure you know the exact definition of that term. For an equilateral triangle, it's quite simple. It's simply a triangle, a three-sided figure, where each of the three sides is equal, or all of the three sides are equal to one another. So we need to construct an equilateral triangle on the given finite straight line AB. So if AB is one of the three sides of the triangle, the other two sides will be equal to AB. So we have to figure out how we can do that using only our definitions, postulates, and axioms to do so. All right? So here's how the solution is done, or the construction is made. The first step that's taken is we start with point A, and we look across to point B, and we imagine that point A is the center of a circle, and point B is the distance to the circumference of the circle from that center. Okay, so we imagine that the line AB is actually a line extending from the center of a circle out to the circumference. And then what we're going to do is, using these 2 points, A as our center and B as our distance, we're going to describe the circle around and back to point B. So we're going to describe or draw a circle from center A at distance B. Okay, we're going to draw that circle. We're able to do that. We're able to do that in geometry because Postulate 3 allows us to do so. Postulate 3 allows us to take this center point and this distance and to draw a circle. Okay? Postulate 3 told us that we're allowed to do that. And so we do that. We draw this circle. Next, we're going to do the opposite. We're going to take point B as a center and point A as a distance. And using B as our center and A as our distance, we're going to describe a circle around center B and back to point A. So we're going to draw this circle around center B at distance A. So we'll draw 2 circles, one from center point A at distance B, this first circle, and then a second from center point B at distance A, drawing this second circle. Okay? We're able to draw this second circle by the same postulate, by postulate 3 again. Okay? If given 2 points, we can use one point as a center of a circle and the other point as a distance to its circumference, and using those 2 points, describe a circle around that center point. That's postulate 3. Now, we have these 2 circles drawn, and what we notice is that these 2 circles intersect at a point up here. That point where the 2 circles intersect, we're going to label that point C. Okay? So that point where the 2 circles intersect, and you can see they also intersect down below here, but we're going to, just for the sake of this construction, we're going to use this top point where the 2 circles intersect, and we're going to label that point C. Okay? So step 1 was, at center A and distance AB, describe the circle. And we labeled that circle BCD by just adding a D. And then at center B and distance BA, describe the circle ACB, with C being a point on that second circle. And I told you that point C is the point where those 2 circles intersect. Now, the next step is, from point C up here, we're going to draw 2 straight lines. We're going to draw a straight line from point C to point A, which we're allowed to do by postulate 1. Postulate 1 tells us that anytime we have 2 points, we're allowed to draw a straight line from one point to the other. So using postulate 1, we're going to draw a straight line from this point C, where the 2 circles intersect, down to point A. And we're going to do that again from point C down to point B. Okay? And both of those lines from C to A and C to B are made because we're allowed to do so by postulate 1 from the postulates. Okay? When we've done that, we have constructed an equilateral triangle on line AB. Okay? So what we were asked to do here, we have here accomplished. We've done it. This is our construction, and we've done what we were challenged to do. Using a given finite straight line, AB, we've constructed an equilateral triangle upon that line. Now, remember, in the study of geometry, our geometrical knowledge has to be absolutely certain. So if I say that I've constructed an equilateral triangle on the finite straight line AB, what you should say is, hey, prove it. Prove that that's an equilateral triangle. And my proof is going to come in part 5, which is the demonstration. Okay, so having completed the construction, we're now going to move on to the demonstration. So now we're going to prove that we have, in fact, completed the task before us in this proposition, and we've done so in a way that's absolutely certain because it's come only from the definitions, postulates, and axioms that were given to us in the elements. Okay? So here's our demonstration. And now one difference that I want to point out is if you get a geometry book, they'll give you a demonstration and they'll write it out and they'll put like the elements that are used, they'll put them in parentheses, but they'll just write them out, and it's really not the right way to do it. What I've done here, as you'll see, is I've actually written each step of our demonstration in the form of a syllogism to show that it's actually sound reasoning being employed to use the elements to prove our construction is true. Okay, so this is one of the reasons why Plato valued geometry so much, is because it teaches us very clearly the syllogistic method of reasoning, which is necessary for the pursuit of philosophical knowledge as absolutely certain truth, or science, as the ancient Greeks put it. So, to prove our construction, the first thing that we're going to do is we're going to start with the definition of a circle. The definition of a circle. And that's definition 15 from your list of definitions. And it says a circle is a plane figure comprehended by one line. A circle is a plane figure comprehended by one line. So by plane, we mean, to put it simply, flat. Okay, it only has length and width. There's no height or depth. So it's a plane figure, and it's comprehended by one line. That one line is what we call the circumference, the line of the circle itself. Okay? So a circle is a plane figure comprehended by one line, to which all lines falling from a certain point to the circumference within the circle are equal to one another. So to put that simply, a circle, the definition of a circle tells us that a circle is a plane figure, or a two-dimensional figure, just length and width, no height or depth. It's a plane figure comprehended by one line, which we call the circumference. And it's a figure where from one point, which we call the center, to any point on the circumference within the circle, every line drawn from the center point to the circumference, every straight line, I should say, every straight line drawn from the center point to the circumference is equal to every other line drawn from the center point to the circumference. So all of the lines within a circle drawn from the center point to the circumference are equal to one another. Okay? We're going to begin with that definition of the circle. Next, our second premise is that point A is the center of circle CDB. Point A is the center of circle CDB. And since point A is the center of circle CDB, then any line drawn from that center to the circumference, like line AB or like line AC, must be equal to one another. And this leads us to our first conclusion. Based on the definition of a circle and the fact that A is the center of this circle CDB, it must be true that line AC is equal to line AB. Okay? So based on the definition of the circle, which tells us that any line drawn within a circle from the center point to the circumference is equal to any other line drawn from the center to the circumference, line AB must be equal to line AC. This is our first point, demonstrated. So we've just proven that this side of the triangle and this side of the triangle are equal. Remember, we have to prove that we've drawn an equilateral triangle. Based on the definition of a circle, we've just proven that this side and this side are equal. Now we need to prove the other side. So we're going to start back at the definition of a circle for our second syllogism, the second step of our proof or demonstration. Again, the definition of a circle is our first premise. Our second premise is that B, point B, is the center of circle CAB. Point B is the center of this circle CAB. Therefore, any line drawn from point B to the circumference of that circle, any line drawn will be equal to any other line drawn. And here we have two lines drawn from point B out to the circumference at point A, and from point B out to the circumference at point C. Therefore, since B is the center of this circle, and these two lines extend from the center to the circumference, line BA must be equal to line BC. So, in this second step of our demonstration, we've just proven that these two sides of our triangle are equal to each other. Okay? In step 1, we proved that this side and this side are equal. In step 2, we proved that this side and this side are equal. Now, in step 3, we're going to begin with Axiom 1. And Axiom 1 tells us that any time two things are equal to a third thing, they're equal to one another. Any time that two things are equal to a third thing, they're also equal to one another. Well, line AC is equal to line AB. We proved that in step 1. We also proved that line BC is equal to line BA. We proved that in step 2. Since those are both true, line AC and line BC are both equal to line AB. Therefore, Axiom 1 tells us anytime two things are equal to the same third thing, they're also equal to one another. Since AC and BC are both equal to AB, then AC must be equal to BC. AC must be equal to BC based on Axiom 1. Okay? So we've proven in step 1 that this side equals this side. In step 2, we've proven that this side equals this side. And in step 3, we've proven that this side equals this side because they're both equal to this common third, this side. That's axiom 1. So that leads us to the fourth and final step of our demonstration. We begin with the definition of an equilateral triangle, which is that an equilateral triangle is a three-sided or trilateral figure with all sides equal. All right? Side AB is equal to side AC and is equal to side BC. All three sides are equal. We've proven that in these three syllogisms. Therefore, triangle ABC is an equilateral triangle. Okay, so here we have our demonstration. Every single step that we've done in this proposition has been either given to us in the proposition, we were given the finite straight line AB, or it was granted to us in the postulates, the elements of geometry. We have postulate 3 and postulate 1, which we used. We've used definitions, and we used an axiom. So every single step that we have taken has either been done by something granted to us, by a postulate given to us, by a definition, or by an axiom. Everything that we've said and done is absolutely certain and proven in our construction and demonstration. And this all leads us to the sixth part of our proposition, which is the conclusion. And here we simply take our determination, which was the task that we were given, and in the conclusion, we simply state that that task has been achieved. So we say here, triangle ABC was constructed on the given finite straight line AB and is an equilateral triangle. And then at the end here, you see the letters QEF. QEF is the Latin phrase which means quod erat faciendum, which means which was to be done. We have done that which was to be done. What was assigned to us in the determination has been accomplished in our construction, has been proven in our demonstration. Therefore, triangle ABC is an equilateral triangle constructed on the given finite straight line AB, quod erat faciendum, which was to be done. QEF is the final conclusion of any proposition that's a problem, because faciendum means to be done. A problem requires something to be done. If we have a theorem, as we will in a few propositions from now, the conclusion will say QED, which means quod erat demonstrandum, which was to be demonstrated. So a problem ends in QEF, and a theory will end in QED. So that's our first proposition in classical geometry. What I'd like to make sure you learn as you work through this proposition, and again, you can watch this video multiple times to go through each step. I move quickly through the lesson because unlike in a classroom where I'm teaching live, in a video, I can move quickly through the lesson and then leave it up to you to simply replay the lesson and watch it again more carefully until it makes clear sense to you. But you can go back through that whole process, see how we worked through all 6 parts of the proposition. From the proposition itself, where we're given a general challenge to be solved in our proposition, what's proposed to us. Then we expose or set out what's been given to us, and we label it to prepare it for our construction. Then we determine what our actual task is for this proposition. In our construction, we work out the solution using either what's given to us or what's granted to us in the elements. And then after we've established our construction, we have to prove every single step of it, which we do here in our demonstration using definitions and axioms. And then finally, we wrap up the proposition with a good conclusion that states that our determination has been accomplished. Okay? This is our first proposition in classical geometry in the Classical Liberal Arts Academy's Classical Geometry course. In Book 1 of Euclid's Elements, there are 48 propositions. So we've got a lot of work to do. One important thing to note before we finish: now that we have solved and proven this proposition, which tells us that we are able, based on the elements alone, we are able to construct an equilateral triangle on a given finite straight line. This proposition is now added to the things that we're able to use in future propositions. So now, after we complete proposition 1, we now have all the definitions, the postulates, the axioms, and we've added proposition 1 to our geometry toolbox, because we can now use and say this because we've shown that it can be done and we've demonstrated it. So now this is an additional element for us to use in future propositions. Okay? And as we continue to go on, we're going to collect more and more propositions that we can then use for future propositions. So our toolbox is going to get bigger and bigger as we go along. I hope that's a helpful guide through this first proposition. Remember, I said there are 6 parts of a proposition, and while most propositions will include all 6 parts, some don't. But we're always going to use this layout to study the propositions and try to establish each of the 6 parts. I hope that's a helpful introduction. Watch the video as often as you need. Study the printed lesson in our online course, which will have more information and allow you to read through the details a little more carefully. And if you have any questions, contact me and I'll happily help you as we get started here. Remember, Plato said that classical geometry teaches us the spirit of philosophy. And I hope that you can see how the standard is set so high so that every step you take and every statement that you make is proven with absolute certainty. That exactness and truth is the spirit of philosophy. I hope that's helpful. God bless your studies.